Good morning, everybody. It is a great pleasure for me to welcome Professor Arun Ross here in the department seminar. He is a world-leading researcher in biometrics and also in the fields of computer vision and machine learning. And he runs a large biometrics center at the Michigan State University, where he is an endowed chair professor. So without further ado, please, over to you, Professor Arun. The stage is yours.
Thank you. Thank you very much. And greetings to all those online as well. Although I can't see you, I'm very glad you joined. And also for advertising this as the Digital Lab colloquium. So thanks for the kind introduction. The talk today is titled Biometrics When Technology Meets the Real World. And as was mentioned earlier, if anyone has any questions, you're welcome to ask of me right away, or we can wait till the end. But please do have your questions in place so that we can have some good discussion as we move along. So I direct what is called as the iProbe Lab, the Integrated Pattern Recognition and Biometrics Lab. We currently have 8 PhD students and 4 master's students. We have graduated several master's and PhD students in the past. It's located in a city called East Lansing in Michigan, and I'm not sure if some of the students online have been to Michigan, but you're more than welcome to stop by at Michigan State University. So our projects are funded by multiple organizations, so I'm just listing some of them here because much of the talk will cover some of these projects. We have funding from National Science Foundation, from IARPA, from NIST, from the FBI, from the Office of Naval Research, Department of Homeland Security in the United States, US SOCOM, and so on and so forth. We are very grateful for their funding and for their support of our research. So let me talk briefly about my research theme. The research theme in our lab is kind of in the field of biometrics can be separated into 3 parts. One is adversarial biometrics, the other one is privacy, and the third one is biometric fusion. So I'll give a brief description of some of these projects, but hopefully there is a theme so that all these things are connected and are not disjoint from each other. So let me start by defining what biometrics is so that there is some degree of tutorial value to this project, but at the same time talking about some of the more advanced topics on this front. So biometrics is the automated recognition of individuals based on their biological and behavioral characteristics and traits from which you can extract distinguishing and repeatable features. So what do I mean by this? So firstly, when we talk about biometrics, we're talking about humans. We're talking about humans being recognized. And we're also talking about biological and behavioral characteristics that are used in order to recognize individuals. Now, the second bullet point is important. We're talking about distinguishing and repeatable features. That means you're extracting features that are unique to an individual and which are reasonably permanent, so that every time you acquire these traits, they do not change reasonably as far as their stability is concerned. So when we talk about biometric traits, we have a number of different traits. Now might be a good time for me to find out if all those online can see my screen, because I did share. I'm assuming they
yes,
can
we
see.
can.
Okay, good.
Yes.
Thanks for confirming. So you have many different biometric traits being illustrated here. You can see fingerprints, you can see palm prints, iris, a schematic of voice signal, signature, face, DNA. We call this as conjunctival vasculature. We had filed a patent in the early 2000s when iris recognition was very popular. At that time, we discovered that you could actually use the vasculature texture pattern that is seen through the sclera in order to perform human recognition. Then you have ear biometrics, you have keyboard typing patterns, you have dental biometrics, gait, the way a person walks, hand geometry, vasculature pattern of the hand or the palm. And you also have what we call as psychophysiological traits. In this case, it's ECG and so on. So you have many different biometric modalities that can be used for recognizing individuals. There are many different biometric applications in healthcare, to border security, to access control on smartphones, in banking systems rather, also refugee services. And obviously this list is not exhaustive, but you have many different application arenas where biometrics is extensively being used. So let me first spend a few minutes giving some basics of biometrics. And then I'll go into some of the topics that we are involved in as far as research is concerned. So what is biometric recognition? You're observing two biometric samples. For example, what you see here are two face images. And you're estimating two numbers. One is the likelihood of observing these two face images, assuming they are of the same person. And then you can also compute the likelihood, so it's a probability distribution, assuming they are of different people. So what you're suggesting here is, in some sense, what are the chances that they are of the same person, and what are the chances is it that these are of two different individuals? So we call this as the likelihood ratio test, which under Neyman-Pearson criteria would give you the optimal statistical test hypothesis. So you can then, for example, take two face images now, and you can compute the degree of similarity or dissimilarity between them, and you can estimate whether they are of the same person or not, and you can do the same for fingerprints. Now we must keep something in mind as I bring the next focal point here. So the first two images are of the same person. The next two images are of different people. They happen to be twins who look very similar. Now, this is where biometric systems can potentially make errors. At the same time, when we talk about the likelihood ratio test, we have to give allowance to the fact that two images could look very similar, but yet might belong to two different individuals. And also that some face images are perhaps very common in the population, that many people might share very similar traits. We can talk about certain demographic groups within which there can be some exaggerated similarity. So all these things the biometric system has to account for. It cannot just look at two images and state that they are similar or dissimilar just based on the features. It has to have some historical evidence as to what the chances are of these two images belonging to different people, and so on and so forth. The last two images here that you see, the question that I have posed here is, are they same or different? And this is an example where a forensic examiner or examiners made some mistakes because one of these images, the one on the left, it's actually a fingerprint image that was taken from the Madrid train bombings, if you recall, several years ago, from a bag of explosives. And you can see the quality of these images. They are suboptimal. But now how do you compare this with another high quality print and be able to make the right decision? So it's a very difficult problem, biometric recognition. In some cases, it's very easy, but in some other cases, it's very difficult. So just to set the stage before going into the advanced topics, what are the components of a biometric system? You have a sensor which extracts a fingerprint image. That would be a sensor. And then you have a feature extractor, which extracts some features from the face image. Or in this case, I'm really talking about fingerprints, so I shouldn't say face, but it's an example of a fingerprint. And then you have a comparator, which compares two sets of extracted features and produces a match score. Now you also have a database or a gallery of stored biometric templates so that the reference data of individuals can be placed here. Now, let me try to summarize what's going on here. You have a sensor which actually captures the physical trait and converts it into a digital form. The feature extractor reduces this to a sequence of numbers. So you have a feature vector, which I'm sure all of you have different feature extraction mechanisms in mind. Then you have a comparator, which actually is doing the matching, trying to compare two sets of features. In this example, you're looking at what is called as minutia points on fingerprints. These are, if you look very carefully at your fingertips, you will see some ridge bifurcations and ridge endings. And if you plot them in some two-dimensional space, you will begin to see some patterns that are unique to an individual. And so these features are often stored in a database. We call it as a gallery database. And then when someone presents a fingerprint image to be matched, you would call that as the probe image. Now, in the last slide, I said there is a difference between feature extraction and matching. But as many of you know, especially in this department, the advent of deep neural networks, or DNNs, has completely changed the paradigm. When I first started working on fingerprints or faces or iris images, I always had to first discover what features can be used in order to represent that particular modality. But now you have deep neural networks that automatically learn what kind of features can be extracted from the input image. So a deep neural network is learning a set of filters, which can then be used to extract features from the input image. And then, as we all know, the features themselves can be classified because toward the end of the deep neural network, you have a fully connected layer, which acts as the classifier in the case of CNNs, for example, convolutional neural networks. So the point of this slide, without going into too much detail, is that deep neural networks and convolutional neural networks have completely changed the paradigm for performing biometric recognition, in that you now have a more sophisticated set of features to perform these matching operations, but you don't have to tell the system what to look for. The system automatically discovers what features to use. So how has this changed the field? So let me give you some statistics on this. One specific statistic. This is from the NIST face recognition vendor test called the National Institute of Standards and Technology. Here I say in the first bullet point, the gallery size is 1.6 million identities. So assume you have a database of 1.6 million individuals, and given a face image, you want to find the right identity. The most accurate algorithm in 2018, which is more recent, provides a false negative identification rate. I'll explain that in a moment. A false negative identification rate, FNIR, of 0.2%. Now compare this with the results in 2014, where the best algorithm gave an FNIR of 4.1%. Now, what is false negative identification rate? It is basically the proportion of times that you don't locate the right identity. So it's a false negative. You're supposed to find the identity, but the system is not able to find the right identity, which can be bad in some cases. If you think of the Aadhaar program and you want to deduplicate an identity, you want to know if the identity has already been enrolled. And if you don't get the right information, then a person can have multiple cards and so on.
So here talking about verification.
This is identification.
Okay.
So here I'm identifying. So I'm not verifying an identity. Although deduplication on the surface gives us the impression it's verification, it's actually an identification operation because you're searching through the database to find out if there is a match or not. So if you look at this simple statistic, and there are so many other numbers I can talk about, this constitutes a 20-fold.
Yeah, sure. Point. So there can be two kinds of errors.
Right.
One is you identify the wrong person.
Right.
And the other one is like you say, okay, nobody really matched.
Right. So
is this a union of the two?
No, this is one of those errors by keeping the other error fixed.
Okay.
So there are two errors, as you rightly pointed out. One is the FNIR, which is what I'm calling out here. But this is at a fixed false positive identification rate. I think it was about 0.1% or 0.01%. I forget what threshold NIST had said. So the FPIR, false positive, which is when I match with your identity incorrectly, that error rate is fixed.
Okay.
And then you're computing the false negative identification rate on this large database of 1.6 million identities. So there are these two errors that are reported separately. So if you look at this number, or the numbers that we provide here, you almost have a 20-fold reduction in false negatives. And this massive accuracy gain, and I'm quoting the authors here, the last bullet point here, the massive accuracy gains are consistent with an industrial revolution associated with the incorporation of convolutional neural network-based techniques into the prototype. if there's anything that is to be said here, it is that CNNs have completely changed the paradigm. But surprisingly, despite the massive advances, there are so many things in CNNs that we don't know about. I'm sure most of the students would agree. There's always something new to do in CNNs. So let me get into this topic of CNNs and see how we have used it in some of our applications. Now, repeating the obvious things, CNNs can automatically learn what type of features to extract from a face image. It's a heavily data-driven approach, which means you require a massive number of training samples. Training can be computationally expensive. You use very expensive GPUs, and so you'll have to compete with those who are doing, Bitcoin mining and things like that, or gaming in order to get those GPUs. But the actual inference or the actual matching is very fast. So it's a data-driven approach, which means the machine learns a concept based on the data that we have supplied to it, and which means many different types of application arenas are possible for CNNs. But now, getting into some of the work that we have done, here we are quoting a 2019 paper, not by our group, but by a different group. And there are two kinds of attacks that they have described, which shows the limitations of CNNs. So at the top, you have what is called as the dodging attack, and at the bottom, you have what is called as the impersonation attack. In the dodging attack, you have two pictures. You think of the same person, so these two images will match. But you can actually have some kind of a hill climbing attack where you can generate a face image like this. I hope you can see my pointer, which will not match with the original image, because this image has been subtly modified so that the matcher refuses to successfully link it with this image that you see here. So although these two matched, this one did not match with this. Now, this is a shortcoming of CNNs, because often the solution that a CNN discovers is not very stable. And so even minor perturbations in the input can lead to drastic outcomes, which, as we all know, can be catastrophic in many applications. Now, if you look at the impersonation attack discovered by, or rather reported by Dong et al., you have two images which are not matching because they're imposters, we call them. But you can actually create an image like this, which surprisingly will match successfully with this image. So it's an impersonation attack. So this shows the limitations of CNNs, because sometimes CNNs work very well, but also they are prone to adversarial attacks. And that is the part which we have to be concerned about. So here is another example.
I have a quick question here.
Yeah, sure.
I'm wondering, in the pre-deep learning era, did people also do studies regarding attacks on the traditional methods, and how successful were they? Or we don't have such studies available?
So that's a great question about what kind of perturbations are acceptable by the system. So normally, so let me try to answer it in this way. The short answer is, of course, yes, they have. They have tried to perturb images to see if imposters can be matched incorrectly, or genuine images can be unsuccessfully matched. So people have done that those kind of experiments. But those kinds of experiments were not necessarily designed to see the limitation of the classifier. But in the case of CNNs, it is particularly designed to expose the limitations of CNN, because the weight vector, which is sometimes 120 million dimension, does experience some kind of singularities in some cases. So there are situations where CNNs are more prone to these kinds of errors, because one could always say that they are overfitting the data and so on. Something which some of the earlier classifiers like SVM explicitly took account of, but not CNNs and so forth. So I'm not sure if I fully answered your question, but those are some thoughts related to what has been done in the past with traditional classifiers. Sure. And why this excitement about CNNs and their limitations.
Yeah, thanks. Yeah, makes sense.
Now, if you start looking at altered data in the physical realm, you can still, encounter these type of problems. So, for example, I hope you can see this image on the lower left. It's a special type of glass that has been designed for this particular user, such that if they were to sport these pair of glasses, actually this image will match with this image on the right. Okay. So this person is wearing a glass, and this glass is specially designed so that the CNN will take this image and say it matches with this image. So, yeah.
I had a quick question.
Yeah.
Sorry. So you said that this would be a singularity, right? So, but what would be the computation required to find it?
It's mostly some kind of a hill climbing iterative method that is used. So the singularity comment was mostly to suggest that there is instability. When a CNN discovers a solution, that particular solution may not have homogeneity in its surrounding. And so therefore, even a slight change in weights can lead to radical change in outputs. But sometimes the vice versa is true, which is small change in outputs, or inputs, I should say, can lead to radical change in outputs, although the weight has been stabilized. And so that's why finding out a stable set of weights is not an easy problem to solve. If you take this video, for example, let me play this. Again, this is not our work, but I'm just setting it up for our work. So here is a person detector. I'm not sure if you're able to see this. There's a person detector here, and it's detecting this person. But if you notice, it's not able to detect this person. Right? You're able to see that? It's able to detect the person on the left, but it's not detecting the person on the right. And why? Because this person has what we call as an adversarial patch that is placed on their body. Okay. I mean, they're really trying to attract attention. It's locating the chair, it's locating the table, everything, but it's not locating that person. Okay. Now look at what the person does. After some time, the person removes that adversarial patch, and now it says person detected. Right? You see that purple patch. So a small patch, kind of makes it difficult for the algorithm to detect the person. But when the patch is removed or altered, then the system is able to successfully detect that person when the patch is moved away. Now, all these speak to the instability of neural networks. Are they really learning a concept, or are they just overfitting the training data? So some of these things are relevant even in the case of biometrics, because if you take a look at all the filters that we have, Photoshop and Snapchat filters and so on, you can take a person with a beard. I hope you're able to see this, and then kind of transform it to a no beard image. You can take a person who looks young, and you can do some operations to make them look old, because you have these advanced filters that are made available. And so this can constitute a security risk even for biometrics, because you can modify images in such a way that it appears to match with the original person, but really has been altered. Or more dangerously, you can alter an image in such a way that it now begins to match with some other person. So all these things constitute a real-world challenge. Another kind of attack that we are working on, not in terms of just designing this attack, but really to deflect this attack, is the spoofing attack. So what is spoofing? You can alter a trait, or you can create a physical artifact in order to spoof another person's trait. So for example, here you can take, and a person can apply makeup in such a way that they match a target identity. So we're not talking about simple, social makeup. These are, this person on the left, she actually figured out what kind of makeup to apply so that she can match with the target identity that you see over here. In this particular attack, which we're all familiar with, someone is trying to unlock someone else's smartphone by replaying the face that would unlock the smartphone, right? So that constitutes an attack as well. What you see over here are fingerprints being created from what we would call as synthetic materials. And so these fingerprints can post the ridges of someone else. So that constitutes another kind of attack. I can go on and say many examples, but what you see over here are synthetic images or altered images that can potentially spoof another person's biometric trait. On the contrary, you also have what is called as obfuscation. So in obfuscation, a person can apply makeup in such a way that they can't be identified by the system. And this does not have to be something very drastic. Using some regularly available accessories and cosmetics, people can make these simple changes. And some of the algorithms will not match the before makeup image, okay, with the after makeup image that you will see over here. They may not be able to successfully match these two images. So what is happening over here are not necessarily subtle changes, but socially acceptable changes, which can lead to this radical outcome of a person not being identified correctly. So you can do the same for iris. What you notice here are printed iris, you have cosmetic contacts, you have plastic fake eye, you have prosthetic, you have glass, and you have Kindle display. All these things can be used to even defeat an iris recognition system. So what we did was we developed some methods to detect these kind of artifacts. If you look at the iris, it is the colored portion of a person's eye. It is very rich in texture. If you look very carefully at into someone's eye, you can actually see those rich textural patterns. And what we used was densely connected convolutional neural networks. Now, many of you might have heard of DenseNet, but let me just give a brief introduction. A DenseNet is a convolutional neural network where every layer is connected to every other layer. And so the final decision is based on a combination of features from all previous layers. So each layer is extracting features corresponding to different resolutions, and you're aggregating these multi-resolution features, which is very important for iris pattern, because if you look at this image that I showed you earlier, the iris has a rich textural pattern, but this rich texture occurs in multiple resolutions. So something like a DenseNet is actually very good for capturing the iris features. And this is very important, especially to students who are using neural networks, because sometimes we indiscriminately use neural networks. We just pick up any neural network that is in vogue and we apply that. But here the point is that it is important to understand the domain in which you're working so that you select an architecture or a design of a neural network that is relevant to the problem at hand. In this case, we're looking at iris images, so we kind of use this DNetPad, as we call it, which is based on dense convolutional neural network. So there are many nice properties for a DNetPad. For example, some of you might be familiar with the vanishing gradient problem in neural networks. Because neural networks, the way they work, error is back-propagated. And the nature of the error is based on the differential. And if you can't take a differential, then you have the vanishing gradient problem. So DenseNet actually mitigates that issue. It encourages feature reuse. It uses fewer parameters. It also smoothens the decision boundaries. So what we did in order to develop an iris pad. Now, if you're wondering about the word pad, it's a presentation attack detection. That is the term that is used in the literature. A presentation attack is something like a spoof attack that I talked about earlier. So if you have large number of training data, you can actually look at some examples here. You can actually detect these type of attacks. Here you're having a bona fide iris, a real iris. Here you're having some artificial iris. And if you start looking at all these images, you will notice that these are cosmetic contact lenses. Not prescribed prescription contact lenses, but cosmetic contact lenses. And these cosmetic contact lenses sometimes cannot be distinguished from real contact lenses, or sometimes even from bona fide images. So our algorithm that we developed using DNetPad actually gives us a true detect rate of 98% and a false detect rate of 0.2%. So this represents a very good high performance, which is based on the specific DNet pad, which is based on the DenseNet architecture. Let me pause there for a moment. Does anyone have any questions regarding all these things so far?
So if I could ask a quick question. So your new system is preventing attacks on old systems, but there could be new attacks that could fool your system. Is that
That's right?
Yeah.
Yeah. So how do we make this generalizable is the question. So one of the things that we did, there are some analysis that we did to show that this is generalizable, which means it can detect attacks that were not used for training. And I'll use this graph to explain this.
Well, actually, that is not quite. Yeah, sure. You need to generalize to, but I'm thinking like, could there be other kinds of cosmetic irises which are designed to fool your system, right? Of course, you wouldn't know if there could be such a thing. I'm just, as a higher level question, is that something to be worried about? Is it a cat and mouse game?
Yeah, it's a cat and mouse game. It is a cat and mouse game. And if you take cosmetic contacts, we did a GradCam analysis of what kind of features are being extracted by our neural network. And if you look at these three rows, the first row is for bona fide images. The second one is for artificial eyes. The third row pertains to your question, which is cosmetic contacts. And what the system is looking at is some features in the lower part of the iris, because sometimes the upper part of the iris is occluded by eyelids and eyelashes. So you're able to see that the system is searching for features on the lower part of the iris that can give away the fact that there is a cosmetic contact lens. So in that sense, it is not learning specific cosmetic contact lenses. It is learning some kind of textural perturbations that are reminiscent of any kind of contact lens. And in fact, we have done several experiments in our paper. I think I cited the paper earlier on. This is the paper with my former student, Renu Sharma. She's now with Amazon, where we actually did that analysis of trying to see whether these systems can detect cosmetic contacts that were not used during the training stage. I hope that that answers your question to a certain extent, but I can give a more involved commentary on why it is generalizable. But that is mostly an empirical way of saying that it is, being able to detect cosmetic contacts that were not used during the training stage. So the other analysis we did had to do with the dense blocks that are used by the DenseNet. In this diagram, I hope you can see this. There are 4 dense blocks. Now, what we did was we extracted the features at the end of each dense block, and we plotted it in 2 dimensions using the stochastic neighborhood embedding technique, T-stochastic, TSNE, very popular paper from some time back. So what you see in each of these graphs is a set of 3 different classes pertaining to bona fide in blue, fake in orange, and green, that would be contact lenses. If you notice, if you use only one dense block, the bona fide, which is blue, and the contact lens, which is green, they're all mixed. I hope you can see that here. But as you start adding more dense blocks, you can slowly see that the green is emerging out of the blue. So if you now revisit the 4 graphs, you will see that the green is slowly being pulled apart, pulled out of the blue. So this is where we notice the importance of adding more dense blocks, although after a certain number, there is no benefit of looking at more dense blocks. Again, this type of analysis is helpful because if we don't do this kind of visualization analysis, then we may not be able to understand, is our system stable? Is it extracting what we think it's extracting? Can we change the architecture? Do we need to add more dense blocks, etc.? But if you look very carefully here, the fake eyes are already well separated from the other classes, right? The green is separating from the blue, but the blue has 2 clusters. Does anyone want to take a guess as to why the blue has 2 clusters? Blue referring to the bona fide, that means the real iris images.
Left and right?
It's left and right. It's left and right. Because the texture of the iris, one could say there should be some kind of, textural aspects, why should it be different from the left and the right? But there are differences because there is laterality to the two. So the DNet pad has actually learned those differences between the two. And it's exploiting that when trying to distinguish between fake iris and real iris. So all these things can be analyzed when we do a more involved visualization scheme. Otherwise, all these nuances will be lost to us. I've already explained this GradCam analysis that we did to a previous question. But as you can see here, for bona fide, it appears to be looking at the pupil in order to determine if it's a real iris or not. For artificial eyes, it's looking at regions outside the pupil. And for cosmetic contacts, it is looking at features which are in the lower part of the iris. So the system is learning something that is unique or peculiar to the three classes here. Okay, any questions on this visualization aspect of CNNs? Okay. So now I'll switch to another research area that we're working on, which is kind of related to, like I said, there is a theme here, but this is a slightly different topic, which is the digital image forensics. So for example, you can ask questions like, which sensor produced this image? So you take a picture, you have a picture with you, and you say, which of these three cameras produced this image without looking at any of the metadata? Can we just look at the image and the camera and make some determination?
So you're not going to look at the PRNU or try to estimate?
So we are doing PRNU actually.
Okay.
So we are doing photo response non-uniformity to do that kind of analysis. But you can also look at other types of features. But PRNU, not despite the fact that it was kind of used about almost 20 years back, still is a very powerful tool for sensor origins. Right? And then you have questions like, is this an altered image? Right? Did anyone apply any filters to these images? Right? Another pertinent question, 4 images here. How are these images related to each other? Okay. Now, these are important questions, and I will kind of give you a little bit more detail on especially the relationship question.
I have a quick question.
Yeah, sure.
So at the outset, so high level thing. So at the outset, say if someone was in the business of producing fake images or fake videos, they could, also simulate these sensor specific aspects like PRNUs into the fake images or fake videos they could create.
Yes, you can inject PRNU signatures into an image in order to make it seem like a certain sensor has produced it. And this is one of the reasons why, as we had this earlier, just now, a few seconds ago, there are other techniques which are not based on PRNU as well. In other words, not depending on just one type of signature, but looking at multiple signatures so that you make it difficult for an adversary to repeat all those things. But you're perfectly right. In fact, we developed a method to synthetically, I'm not talking about it in this presentation, to synthetically inject PRNU so that the detector is confused and doesn't know which sensor produced that image. But the reason why we did that was for privacy purposes. Photojournalists, they take pictures and they publish it. And sometimes it becomes dangerous for them because people find out which photographer took those images because they can link it to a certain camera. And so in order to ensure privacy, especially when they're taking pictures in very sensitive areas where there is blackout and things like it, we developed a method by which these images are slightly altered so that the image content is not compromised, because that becomes a liability in the code of law. In the code of law, they would say, well, the image has been altered. So we want to retain the semantic content of the image, but we change or we perturb the PRNU noise and things like that. Yeah. So the short answer is, having multiple set of features is one way to kind of avoid this issue where someone is deliberately trying to inject noise into the system. So another kind of attack is a digital morph. So let me just explain it using the image panel on the left. Do you see here it says ID1? That's person 1, and you see ID2, person 2. And now do you see the word morph here? Now you see a picture of a person. Now that person has been created by morphing ID1 with ID2. Okay, now what is the problem with that? Now the problem with this is that the morph image will match with person 1. It will also match with person 2. So a single image actually is hosting two identities. And this can be a problem in passports, because the same passport can be used by multiple individuals, or the same ID card can be used by multiple individuals, because the picture will match with these multiple identities. So this morph attack has taken on quite a bit of life on its own in the field of biometrics. And there are many competitions being held both to generate morphs that are realistic, but also to detect morphs so that the attack can be deflected. We all know deep fakes. I don't have to say much. Originally, the word deep fake was used to suggest that you have a person and you replace their face with someone else's face in such a realistic way that it appears that this other person is doing all these other tasks that the first person was doing. So I'm not sure if you have checked out this website, thispersondoesnotexist.com. But if you go to this website and you keep refreshing, it starts generating fake faces, which can look very realistic. So all these three images that you see here were generated using GANs, generative adversarial neural networks. And they are all not corresponding, or at least should not be corresponding to a real person. So you can see the wide variety of problems that biometric systems have to reckon with. On one hand, you want to find out who the person is. On the other hand, that picture could have been synthetically generated or synthetically altered. And so how do you, kind of manage biometric systems under these diverse conditions? So that is one important question that we have to deal with. Now let me talk about something which is more subtle, what are called as near duplicates, subtly modified images. So if you see this image on the left, you have brightness adjustment, images that are slightly altered. This is gamma transformation. These are images under rotation. Now the question here is, which is the original image and how are these images related? So let me give this example. You have 5 images, 1, 2, 3, 4, 5. Can you actually come up with a tree structure like this, which says that the image number 5 is the root image, and then image number 2 is derived from 5, image number 3 is also derived from 5, and image number 4 also from 5. But image number 1 is derived from 4. So we don't know what transformation was applied for 5 to be modified to 2. We don't have to know. But we want to establish this relationship. It's very helpful in analyzing the web, because sometimes people take one picture, make some alterations, and put it in a different website. And then someone else takes that image, makes some more alterations, and puts it in a third website. Now, if you get all these similar looking images, can you actually find out which is the original image and which are the modified images? This tree-like structure is called as an image phylogeny tree, or IPT. So IPT is where you take a set of 5 images and you convert it into a tree-like structure showing the relationship between these images. It has many significant benefits. You can find image tampering. You can also find out how these images are related. You can also answer the question, is this image originating from a single source image, or is it originating from multiple sources? So image phylogeny tree, I won't go into the details. It's very involved. We have 2 or 3 papers on this topic, but I just want to give you kind of an outline of how we approach the problem. It's a very difficult problem. What is the problem? You're given 5 near duplicate images, which means they look very similar. From this, we compute an asimilarity matrix, which shows the asymmetric relationship between these images. And then we apply a tree spanning algorithm, which can be any standard tree spanning algorithm, in order to construct the image phylogeny tree. The most difficult part of this exercise is generating this asymmetric matrix. Let me explain why. Firstly, there is a large number of photometric transformations. How do we know what kind of photometric transformations are being applied? It's an infinite set of features. Each transformation has multiple parameters. Take the simple Gaussian transform. It has a window size, it has variance. And then each of these parameters has multiple values. Are you using a 3x3 window or a 5x5 window or 9x9 window? Secondly, how do you distinguish between A to B and B to A? Because both are different. If A is being transformed to B, we need to tell that A has been transformed to B, not that B has been transformed to A. So in order to handle all these challenges, what we did was we came up with a generic parametric transformation function. Now, this function does not make any assumptions about how the two images would have been altered or how they are related. We don't say that one brightness was adjusted and so on. We don't make any assumptions like that. So it's a generic transformation function. And we estimate the parameters of the function in both directions, from A to B and B to A. And then using a likelihood test on the parameters, we say which of those two cases is more likely, A to B or B to A. So here's the transformation function. You have the source image A of u comma v. We apply a transformation function which has taken it to B of u comma v. We don't know t. But now, since we have a fixed set of basis functions, we are parameterizing t with alpha. So what are some of the choices for these basis functions? We can have polynomials, we can have wavelets, we can have RBFs, radial basis functions, and so on. All of these are parametric. So now the problem reduces to the following. You're given the original image, you're given the two images B and A. Now estimate the parameters that are connecting A to B, and they can pertain to any of these existing functions.
So are you taking a linear combination of these basis functions?
So in our case, each of these functions is viewed as a basis function because, for example, if you take the Legendre polynomial, it's got a summation of this expression. So those are the basis functions constituting that. Similarly, if you take something like a Chebyshev polynomial, there is a summation factor which takes into account some of these terms which are then added. So this problem now reduces to something manageable. You're given A and B. You basically assume, let's say it's a Legendre polynomial. And now you kind of say if A goes to B, how will B prime look like when you model A to B transformation using this Legendre polynomial? Similarly, we can do that for Chebyshev, for Gabor, Gaussian RBF, or bump RBF, and so on. So this makes it very simple, but still the problem is challenging, but makes it simple because the way we have reduced it is that we are modeling the transformation in both directions, resulting in two sets of estimated parameter vectors, and then using a likelihood ratio based on training data to estimate which direction is likely, A to B or B to A. Okay. So we did many tests. I don't want to go into too much detail, but identifying the root is the most difficult problem because you want to know which is the original image from which others have been assessed, have been derived. And so we got a performance of around 80%. And on the surface, it doesn't seem to be a good number. You want this to be 95, 99. But you'll have to keep in mind that the previous best was 47%. So effectively, using our technique, be it Legendre, Chebyshev, Gabor, Gaussian, or bump RBF, our method has substantially improved the state of the art.
So how do you get the root once?
So once we have the
from the tree.
So we do a depth first search to construct the IPT. So therefore, you get the root as a consequence of that. Now the second problem is, assuming you have the right root, can you still construct the tree correctly? And so our performance numbers are 66%. But again, if you look at the state of the art prior to that, it was 18.75%. It's a very difficult problem. We don't deny that. And that's why these numbers are low, but it kind of says there is a way in which this can be approached. Since the world of transformations is infinite, by using these basis functions in conjunction with likelihood ratio tests, you can at least have some way of deducing the root and the the IPT itself. Any questions so far? Yes.
How do you choose those specific functions to be the basis function?
Yeah, that's a good question. So we didn't have any specific way of selecting it. The only thing I can say, which we describe, this was done with my former student, Sudhita Banerjee. She's now a research assistant professor at New York University. So we looked at the literature to see what kind of functions have been used to model image transformations. And so that was the basis by which we selected these particular functions. So it was not a mathematically driven decision. It was mostly what has already been done in the literature and understanding that if they have been successfully used to model images, that they might have some application in this particular field as well.
You know, choice of the number of basis functions can have a lot of impact.
Yeah, perfectly correct.
I've seen this in a different application.
Yes.
This kind of thing.
Yes. Yeah. So the value of n, right?
Yeah.
The value of n is the most thing. So one thing I must mention, I'm glad you asked that question. Many of the transformations that we considered, the end purpose was to have near duplicates.
Okay.
That means the images are not drastically altered. Sometimes when images are drastically altered, you know that they're altered, and you know, okay, this one is not the original image.
Right.
So these are subtle modifications, and that is why the value of n is very modest. I forget what we say in the 2019 paper that Sudhita wrote with me, but I think we had in some cases n as low as 5.
Nice.
Because anything greater than 5 would mean perturbations are so large that they no longer fall under the realm of near duplicate images. And why are we considering near duplicate images? Because potentially those are the images that can be used to subtly attack a biometric system. Whereas radically modified images are much easier to detect anyway. So let me move on to a couple more topics. I think I have a few more minutes. I just want to speak a little bit about deep talk. This is again falls under the realm of altered data, but for good purposes. Now we developed this engine called Deep Talk. It's a speech recognition and speech synthesis method. And what does Deep Talk do? Well, if you have a certain news report to be reported, it articulates that in the voice of your favorite newscaster. And the reason why we did that was we discovered that sometimes people are able to believe news when it is being articulated by someone they trust. And so the same news article, when read by two different newscasters, can produce a different response in an individual because they happen to trust one more than the other. So what we tried to do was try to develop an engine which could take text and articulate it in the voice of a specific newscaster. To do this, we have the Deep Talk encoder, which produces a Deep Talk embedding. And then we use the classical tachytron, this is not our work, which can synthesize a spectrogram based on the target text that has to be articulated. And this synthesized spectrogram can be put into a wave RNN. It's a vocoder, again, developed by someone else, and that produces the synthetic output voice. Right? So what you're seeing here is that our primary contribution is how do you take a target speaker who has to be mimicked and discover an embedding that is unique to them, so much so that when they Secondly, we have what are called as global style tokens that is already available in the literature. And what this does is it imparts a style to a person's voice. It imparts stylistic features so that the person has a certain speaking rate, a certain kind of animation, and a certain type of pitch. So let me give you one example of how this works. So you have a news article that has to be read. And let's say there are two newscasters. One is Hannah, the other is Ted. First, let's listen to Hannah's original voice. So that is Hannah's voice. Now, this is Hannah reading out this news article, but this is not the real Hannah. It is actually the deep talk engine that is doing that. So let's see how this sounds as this engine is reading out this news article. So in our experiments, which is there in this ICASP 2021 paper, we actually show that both voices are correctly mapped to Hannah. And also that now Hannah is able to, the deep talk of Hannah is able to articulate this news article. Now, certainly there's much work to be done on the stylistic part, but if you look at Ted, and now this is the engine. So again, the identity matched, but still there has to be some work done on the stylistic aspect of the feature. So the point of this is to say that in some cases, altered or synthetic data is problematic. In some other cases, altered or synthetic data is actually good. It's acceptable because it can be used for some positive purposes. So this brings me to my last topic. So I'll just take a few more minutes, and then I'll be happy to answer questions. I hope you have some questions, especially the students. If there are any online, it will be nice to hear your questions as well. So I'm not sure how many of you have heard the word soft biometrics, but soft biometrics refers to features such as gender, age, ethnicity, or health that are not unique to an individual, but which give additional information about an individual. Now, modern algorithms can estimate age, gender, and ethnicity automatically. So which means you can develop a trained classifier or a trained regressor that, given a face image, for example, can deduce all these attributes. We call this as attribute classifiers as well. You can also do this for iris. For example, based on this iris image, an attribute classifier can suggest that this is a male, a white male, that this image was taken using an A-optics camera. It can even give a commentary on the iris texture, saying that this iris stroma is plain textured, and can also offer forensic value. It can say that because this is a highly constricted pupil, that the external lighting was very strong. So by using a single image, you can extract all these attributes without having a matching image at play. So one could view this as saying, well, this is great. It bridges the gap between human and machine description of data, because humans are likely to describe data in this fashion. But on the other hand, one could argue that it compromises privacy as well. So now the question that we ask ourselves is, how can we enhance privacy? Now take another example here. From a face image, one can assess genetic disorders. So just from a face image. And there is a product called Face2Gene, which does exactly that. It takes a face numerical feature and then maps it to a syndrome gestalt, and then potentially revealing some genetic disorders in a person. Now, clearly one can see the benefits to science, but one can also imagine the compromise of privacy that can come about. So this is where we came up with this notion of controllable privacy for face images. This is the last topic that I will speak about, where the user who's providing the data should have some way of saying, well, you can use my face image for recognizing me, but don't use it to estimate age, gender, or race using automated algorithms. So the focus is on automated algorithms. You don't want automated algorithms to extract some features, but you allow them to extract other types of features. So here is what we developed, a concept called semi-adversarial neural network back in 2018. What this does, it's an autoencoder. It takes an input image and creates a perturbed output image such that this image can be successfully used by a face matcher, but cannot be successfully used by a gender classifier. So that's why it's semi-adversarial. It is adversarial to a gender classifier, attribute classifier, but it's not adversarial to a face matcher. So the concept is fairly easy to understand. You have the original image space. What the semi-adversarial network does is it maps this to a transformed space where the two classes are mixed with each other. But there's an additional constraint that we impose, that the identity has to be retained. Now that is the challenging part. So we can't just perturb the image and say we are successful. You still want the face matcher to work well, which means the biometric content cannot be smeared. So we developed the SAN model as follows. It's a convolutional autoencoder. The input is transformed to an output. X is transformed to X prime. But X prime, the output is supervised using an auxiliary face matcher. We say auxiliary because this is used during training, but during testing, you don't need this. And you can also have an auxiliary gender classifier, which is supervising the output in such a way that the face matcher has to be successful, but the gender classifier has to be unsuccessful.
So can I ask actually the same question as before in some sense? So this is for the specific auxiliary gender classifier, right? If somebody comes up with a different gender classifier trained on your perturbed data, they might still be able to identify gender.
So in our case, this is generalizable. So in fact, the reason why we use the word auxiliary is to separate it from the eventual set of face matchers and the eventual set of gender classifiers on which this method is evaluated on.
But my question is, could somebody, did you try training a gender classifier which is trained to work with the output from your system?
Yes, we have. There are many SANs that we have developed over the years. The basic SAN is from 2018. Since then, we have developed what is called as a flow SAN, and then we have a privacy net. In a flow SAN, the image is altered in such a way multiple times so that there is a probabilistic output, and so that at least one of these outputs will confound an arbitrary face classifier. So we did that kind of an experiment probabilistically to demonstrate that even if you were to develop a gender classifier based on the perturbed data, that you can still generate one version of the output here that can confound that particular classifier that has been developed from the perturbed data. So that is one way of looking at it. The second way of looking at it is that anything that is learned on the perturbed data may not be useful in the real world. Because in the real world, you're given a face image, and you want to say assess its the race of the individual. Say you want the original data, not the transformed data, because you don't have the transformation function, or you may not have the transformation function. So I hope that partially answers your question. I think on one hand, can we develop a new face matcher or gender classifier? The answer is yes. But using our flow SAN, you can even confuse those newly developed classifiers. And secondly, from a practical standpoint, if there is an algorithm that is working on perturbed data, then it's very unlikely to work on the original data because it has not been designed for that. Thereby, its practical utility is a bit lost. So we move this to multiple attributes, not just a single attribute. Say, for example, only gender or only age or only race. We kind of have this as multi-attribute privacy. We use a regular cycle GAN. And what this regular cycle GAN does is that you can take an input image and you can give a target set of labels. You can say that this input image should be transformed such that it's a female image of a Caucasian and whose age is middle-aged. So that's why you have this target label, which is denoted as CT. Now, the trick here, I won't go into the mathematical details, is how do we develop the loss functions for the privacy net? And like any GAN, this has a discriminator, it has a generator, and so we came up with specific loss functions in order to deal with this kind of an objective function. for the privacy net. We call this as the privacy net, which is different from the flow stand, which I discussed for the previous question. So let me illustrate this as follows. So here you have a face image. The original label is 011, 0 standing for female, 1 for middle-aged, and 1 for Caucasian. Now let's say the target changes to male, middle-aged, Caucasian. So what happens to the original image? It is transformed. And I'll show you some results, quantitative results shortly. Now, if you change this to female, old, Caucasian, that means you've only changed one of the labels, then the image moves in this space. It transforms. Or if you say female, middle-aged, African, for example, then it would change in this way. In other words, you can change the target label, but in some cases you can change 2 attributes at a time. You can say that this has to become a male, old, Caucasian. Now I know here the hairstyle might give away, or the facial accessories might give away the gender, but most face recognition algorithms do not take the hairstyle or the ear accessories into account. It's just the face. So from that perspective, these attributes are indeed confounded, but please keep in mind that the identity has to be retained. That's the most important thing. Otherwise, I can make these changes using any classical GANs. And so there's the other objective function, which is to make sure that the face matching is feasible. So if you take this transformation, or these transformations, this is what privacy net does. M for matcher, G for gender, A for age, R for race. Originally, all these are correctly classified. But when you use privacy net, you can specify, for example, that the age has to be confounded, or you can even say that the gender and the race have to be confounded, but that the matcher has to work and the age classifier has to work. Or you can have a situation like this where you're saying that the matcher has to work, but the gender, age, and race should not work. Right? Age classifier should not work. So what you're seeing here is that the image is being transformed, keeping these multiple objective functions in mind. So here's an example with match scores. You have the original image, and you're changing the gender and the race information. A classical GAN would produce an image like this, the one on the right. But if you look at the match scores using 3 different matchers, the match scores are very low when you match it with the original face image. Privacy net now generates an image like this, but it has the match scores are fairly high compared to these match scores. A match score indicates the degree of similarity in identity. So you want this to be high. And here's another example, gender and race being modified. A classical GAN, the match scores fall down. Whereas in the case of privacy net, the match scores are still fairly competitive. And in fact, we did some experiments to show that the loss in matching accuracy is not substantial. Although the confounding attribute is sufficiently confounded, you can still use this for matching purposes. Okay. So just to summarize what I informally discussed with all of you, really 2 topics, image forensics and privacy. Both the commonality here is that images are being perturbed, that images are being slightly modified. In some cases, that's a bad thing, and you would like to detect it. In some cases, you view it as a good thing because you have controllable privacy. And so we saw the following: is this image a spoof attack? Which sensor did this image come from? Has this image been digitally tampered? What is the relationship between a set of images? At the same time, these perturbations can have some positive ramifications, especially when you want to impart privacy, and especially when you want to impart controllable privacy. So I'll stop there. I think my time is up. But I just want to show you 2 short videos for fingerprint anti-spoofing and face anti-spoofing that were developed as part of a larger project with my colleagues. So I'll first play this fingerprint spoof buster and then the face, and then maybe we'll have a few minutes for some questions and answers. It's a real finger. The system says it's a real finger. These are fake fingers. fingerprints, I must say. It looks like a real finger, but it says it's a spoof finger. So you can clearly see that the system is able to detect a spoof, even though to the naked eye it appears to be a real image. Same thing for face. I'm going to play this. You'll see some faces. If there is a green border, it means it's a real face. If there is a red border, it means it's a fake face. But let's see how this algorithm works. So it's a real face that a person is acquiring using a smartphone. So you see a green box. So that's how it should be. Again, a real person interacting with the system. It should be a green box. And now again, a real person. These are some of the students who worked on these projects. And now it is not a real face. It's a real person, but it's a printed face, and it has a red. Now this is a replay attack, and the system actually says it's a fake face. We have a lot of mannequins in our lab now, and so it says it's not a real face. Other types of attacks, the system is able to say, it's able to detect the face, but it says it's not a real face. And some exotic makeup application, even the system is able to say that this is not a real face. So I'll stop there, and if you have any questions, I know I'm meeting some of you later on. I'll be happy to answer questions then, but now is a good time to ask any additional questions you may have.
So for the liveness detector, I mean, motion is one of the very primary cues, I suppose.
Right.
So, but if you're playing a video of a person, like we showed the iPad, isn't that the most challenging?
So surprisingly, the most challenging is actually the makeup attack. Sorry, I take that back. The mask attack, where someone wears a mask on their face.
See.
That is one of the most difficult attack vectors that we have encountered. Going back to the display attack, that is in fact one of the easiest attacks, because when you play it on a screen, there are some artifacts that come about because the screen is refreshing at a certain rate, and so that leaves a signature which can be detected. So yeah, the mask attack is the one where we failed many different times. Yes.
So you have been in this research for quite a long time.
Yeah.
So you have seen the transition from traditional way of approaching the problem towards the deep learning approach.
Yeah.
So what are your general thoughts about its applicability in research and the reliability in the application?
Yeah, good question. It's an open question, right? I always tell my students one thing, right? More than deep learning, you should have a deep understanding. And sometimes I find, and I don't want to generalize this, that many of the new researchers who started out their career with deep learning, they know a lot of things about deep learning, but sadly they may not have a deep understanding of the domain in which they're working. I'm not generalizing, and I never will, but I'm just saying I've seen a pattern even in CVPR papers and so on, where the focus now is on what kind of parameters should I have, how do I train, and these are valid, legitimate questions, but in the process, the domain knowledge is lost. So my recommendation is always to have a good balance between the two. Deep learning has been successful, there is no doubt about it. So we don't want to throw it away. It has tremendous promise. I think it goes without saying that it's perhaps one of the greatest discoveries in machine learning over the past few decades. So having said all these things, it is also equally important to understand the domain where it is being used. Fingerprints or face or iris, it is good to get into the biology, for example, of the biometric modality. If it is something, a space telescope, which is taking pictures of galaxies, it's good to understand some of the physical attributes, not the physical attributes, but the physics-based attributes and the astronomy-based attributes that are being revealed in those images, because then you can develop a more intelligent, deep learning system. The second point I'd like to make is that deep learning requires massive amounts of data, and in many cases, massive amounts of annotated data. So now the question is, what happens if you don't have massive number of data points? Then the solution is to do transfer learning, right? You learn in one domain and then you fine tune using fewer samples from the other domain, because certain filters are applicable in multiple different domains. But still the fundamental question remains. If you do not have sufficient data to train your deep neural networks, then what are some of the ways in which those things can be handled? The third question is computational power. You can imagine, I think CVPR deadline is November 15th or so, I think. I could be wrong about it. I don't want to mislead anyone because I know you're all trying to get your papers done. And, our students had to start 3 months in advance to do the experiments, which was unheard of, previously when I, did research in this field 20 years ago. Because now, the training process can go on for weeks, and then you change one parameter, and then you run it for some other length of time. So all these things have to be taken into account. How can we train neural networks more efficiently? How can we work with limited amounts of data? And how do we develop domain knowledge? We don't want to throw away domain knowledge and rely purely on a data domain approach. So those are some of the comments that I have to your question. Yeah, sure.
Related to fingerprint biometric and iris scans. So how important are the local statistics and compared to the global statistics that we are doing pattern recognition?
Yeah, that's a great question. I think both set of statistics are important. There are some, if you take fingerprints, there is a global shape and structure to it. But the discriminatory information comes from minutia points, which are local. And so we don't want to miss out on the global statistics like the rich flow, singularity, and so on, at the same singular points, I should say. But at the same time, we understand that the discriminatory information, the distinguishing information is coming from local regions. So you want to have a good balance between the two. And I think that is true for many kinds of objects, not just for fingerprints, where you need both global and local features. Yeah, sure. Go ahead.
So currently, we have been advancing toward quantum computers, and people are talking about quantum cryptography, post-quantum security. So what application or what impact do you see in biometric security, in terms of biometric security with quantum?
Yeah, that's a good question. I think the biggest impact will be on, as you said, homomorphic encryption and any other kind of encryption schemes, any other kind of encryption scheme which can potentially be easily broken. I think the difficulty is actually developing quantum computers. The theory is there. The investment, I don't know. But to be very honest, I've not really seen anything that is exciting enough to say that there will be a quantum computer next year or so. So I think there is a long ways to go until we, develop that kind of machinery. Maybe something else will serve the whole thing and kind of say that there's new technology. But at the same time, let me be measured in my comments. I think certainly quantum computer will change the game, especially for encryption. And I think that question will also be relevant more to the cryptographic community, because I think they are the ones who have to reckon with all these things eventually. But, any other question from those online or anyone else? I think I'll be meeting with some of them later on.
Yes.
There.
Yes.
So you're welcome to ask questions later, or you can even send an email. But let me just wait for 30 seconds if anyone has any questions. Sometimes they hold on to their questions. I think. So yeah, go ahead.
We are mostly investing towards human biometrics.
Right.
Are there research going on animal biometrics?
Oh yes, yes. Lots of research, especially identifying dogs, identifying cats, identifying fish, cattle, primates, because there is smuggling of exotic animals, identifying them. So there is much work going on in that field as well. So it's not just human biometrics, although in human biometrics is where much investment has been done and much work has originated from. But there are these other periphery areas where people are looking into using biometrics as well.
So you show an example
Uh-huh.
of biometric data being used for genetic identification.
Correct.
So are there any similar applications, like most applications to biometric data apart from being applied in security?
Could you repeat the last part? I couldn't quite
So
catch.
are there any more applications of biometric data apart from being applied in security?
Oh, you mean by definition, biometrics is for recognizing individuals. So I think what your question is, well, you can potentially use it for analytics. So yes, so the genetic part is more of an analytics part than a pure biometrics part. There are other applications also where one can take a biometric image or a biometric signal and extract information about the environment. So in the case of iris, you can potentially look at the iris and see where the person is looking at, and actually sometimes create an image of the room in which that person is located. So there are these additional forensic utilities that come about where biometric data is used for purposes beyond what it was intended for. That's a great question because we do a lot of work on digital image forensics. So we always ask the question, what kind of additional pieces of information can be gleaned from biometric data? Because it's more of a privacy question that comes along.